The last thing we need to learn about in the polynomial arithmetic unit is to still work on factoring, but there's actually a very specific type of factoring that makes some problems super duper easy. And it's called the difference of two squares or difference of squares formula. So we're going to be using this formula. It is on your formula chart. It's formula number 2. So it's not something you have to memorize, but it is something so easy to memorize that you might as well just memorize it. Here's the formula, and I want you to circle this right here. A squared minus b squared automatically factors to a plus b, a minus b. So again, this is called the difference of two squares. And if you look at the acronym for that formula, the difference of two squares, I like to call it the DOTS formula. Difference of two squares, the DOTS formula. Are y'all cool with that? Okay, so it helps us factor these specific expressions without having to do an X puzzle and all of the swing and divide steps I taught you a couple lessons ago. Okay, but you can only use it when, bless you, very specific things happen. You can only use it when you have a difference of two things that are what are called perfect squares. So difference means that what is going to be in the problem, an add or a subtract? Subtract. Okay, and it says difference of 2, so can there be 3 things in my equation? No. Just 2. And if it's a perfect square, that means it either says x squared or y squared, or the number is a perfect square. Do y'all know what perfect squares are? No. No. What is 2 squared? Oh my gosh, what's 2 times 2? 4 is called a perfect square. What's 3 times 3? 9. 9 is called a perfect square. What's 4 times 4? 16. 16 is called a perfect square. So it's these numbers that perfectly have a square root, that a number can be squared and get that number. And if you notice that your equation, your expression there is a subtract sign with 2 things, and those numbers are perfect squares, you can take the shortcut. You can use this formula. Okay, so let's just make sure we know when to use it. This first example here, x squared minus 49. Are we subtracting? Yes. Okay, yes. Yes, we are. That should be a resounding yes. Are there 2 things? Yes. Great. Are they both perfect squares? No. X squared is yes. X squared is for sure a perfect square. Is 49 a perfect square? Oh, yes. 7 times 7, right? They're both perfect squares. 7 times 7 is 49. So this one, we would be able to use the formula. And I'll talk about using the formula in a second. We just need to identify when we can use it. For the second one, there's 2 things, and they're perfect squares. This is 5 squared and x squared, and then 16 is 4 squared. But am I subtracting? Can I use this formula when there's a plus sign? No, we can't use it.
So if there's a plus, it's automatically...
If it's a plus, it's automatically something that we have to use a different type of factoring. This only works for when there's 2 things that we're subtracting and they're perfect squares. But let's look at the middle one. 49x squared minus 9. Am I subtracting? Are there 2 things? Are they perfect squares?
No. Wait, yes.
49 is what? 7 squared? So I have 7 squared x squared. And what's 9?
3 squared.
3 squared. If every single part of it can be squared, then that is a yes. We can use the difference of 2 squares pattern. Okay, the next one. Am I subtracting?
Yes.
Are there 2 things?
Yes.
Are they perfect squares? So well, 16 is 4 squared, and then I have x squared. Is 10 a perfect square? No. So this would be a no, because this 10 right here is not a perfect square. If you're struggling to figure out if things are perfect squares, then you need to start using a calculator. If you don't recognize these numbers, all you would need to do is take the number and do what's called the square root of that number. If it comes out to a perfect whole number, it's a perfect square. But if you do square root of 10, it's going to be some decimal, 3 point something. I don't even know what it would be after that, 3 point something. I'll say 3.1. Okay, that is not a perfect square. All right, let's do the last one. Am I subtracting?
Yes.
Are there two things?
Yes.
Are they perfect squares?
Yes.
Yeah, 36 is what?
6 squared.
6 squared, and then we have x squared, and then I'm going to subtract 3 squared, and then an x. Wait, are they all perfect squares?
Yes.
They both have the same variable, so this is not a perfect square, but this does have a GCF. I'm so glad you noticed that. Both of those terms share an x.
I told you.
He said it louder. He gets all the credit.
But I.
Okay, so it has to have every single part has to be a perfect square. So this is why it's a no. Okay, so let's start actually using it. Recognizing that you can use it as half the battle, then we actually have to use it. Yeah, what's up? On the last one? Okay, so 36 is x squared. X squared is x squared. 9 is 3 squared, but this has an x attached to it. Is that a square?
Oh,
No, so we can't use the pattern.
so it has to have.
Every single part of it has to be squared, yeah.
What about this one?
Which one?
What about the one in the middle? We said it was yes.
Is it every part of it squared? 49 is 7 squared. Then you have x squared. Correct.
So if there is an x, it has to be.
On this first practice problem, we're going to rewrite each expression to find their factors. So, before today, if I asked you to factor, you would have had to set up an x puzzle and then use swing and divide to find the parentheses factors. But today, you can ask yourself before you start, is this the difference of two things that are perfect squares? This is x squared minus what? 5 squared. Okay, great. If you notice that that's the case, this is where the pattern comes in. The pattern says, if you look up at the top of your paper, that if you have a squared minus b squared, that it automatically factors to the first thing plus the second thing, and the first thing minus the second thing. Boom, I'm done.
Huh?
What? I factored it. Do y'all see that pattern?
Wait, so you said first thing plus.
Okay, look at the top of your paper. It says a squared minus b squared equals to a plus b, a minus b. So it's saying if you have two things that are perfect squares that we're subtracting, you can take the first thing plus the second and the first thing minus the second and put them in parentheses. Those are your factors.
Okay.
Yes? Can we do the next one? All right, we want to factor. And remember, when you see that we want to factor, we're trying to find the parentheses version of this expression. But I noticed that there's two things, and I don't want to multiply 49 and negative 36 because that number is going to be disgustingly large. We can try to use the difference of two squares. Am I subtracting?
Yes.
Are there two things only?
Yes.
Are they both perfect squares?
Yes.
Yeah, 49 is 7 squared with an x squared. And then 36 is?
6 squared.
Great. So it should automatically factor, since it meets the pattern, to the first thing. What's my first thing?
7.
7 and?
6.
What? No, the first thing. 7 and?
7.
7 and x plus the second thing. And then the first thing plus, minus the second thing. Voila. I factored it. These totally still work if you set up solve an X puzzle and do swing and divide, but like, yuck, this is way less work, right? This is a shortcut formula that you can use, but it only works in very specific examples. Let's try this one together again. Can I use the difference of two squares pattern?
Yes.
How come?
Only no, you know. Because 121 isn't.
It's again? It's 11 squared, right?
Okay, I hear some arguments, so I like it. So we have subtracting, we have two things, and I can write everything as a perfect square. 9 is 3 squared, and 121 is 11 squared.
Really?
Uh-huh. 11 times 11 is 121.
Oh.
So if I got this part set up for you, can you write the factors?
Yes.
I want to see if you can do it without me. All right, so this one would have been 3n minus 11, 3n plus 11. Hold on, I want everybody, you probably wrote yours a little differently than me. Does that matter?
No.
What did you guys write on your papers?
I did plus and then.
Does it matter the order?
No.
Not for multiplication. So if you put 3n plus 11, then 3n minus 11, that's the same thing. Okay, last one over here. First things first, I want to factor this. Can I use the difference of two squares?
Yes. Why no. Yeah, it's a plus.
Wait, I can?
Oh, you can't.
Can I use difference of two squares when there's a plus?
No.
No, so we'd have to revert back to other methods of factoring, which meant we look for a GCF. We set up a next puzzle. I won't make you actually do this problem because, in fact, this one is not factorable. Nope, there's no number that divides into 16 and 9. There's no common R between them. There's no GCF. It is not factorable.
And there's a plus.
And there's a plus. Okay, all right, let's flip this thing over. All right, so we've kind of talked about everything you'll need to do what's called factoring completely. Remember, factoring is the key word to make us think about wanting to put them in the parentheses, factored form. So here is the thought process you should take every single time you do one of these problems. The very first thing you do is you stop and you check to see if there's GCF. I like so much so I'm drawing the stop sign on here. You got to stop and make sure there's no GCF. If there's a GCF, you got to take it out because it'll make your numbers much smaller and much easier to work with. After that, you have two branches. Whoa. Once you have the GCF and the leftovers, you're going to take the leftovers and either look to see if it has two terms, which means we're doing the difference of two squares. Or if it has three terms, you're going to set up and solve an X puzzle and use swing and divide. Just for good measure so that these are good notes, how do I set up an X puzzle? You just do it. What goes in the top? A times C. What goes in the bottom? B. And what's in my denominators? Okay, good. So we know how to do this part. And there it's on our notes just in case we forgot. So we're going to go through these 6 polynomials here and we're going to factor them all completely. As completely as possible. So you're going to walk me through these steps every single time. Okay? I ask you to factor. What's the first thing I check for? Oh, wait. Well, look at the top of the paper. What does it say to check for first?
Stop and check for
GCF. Is 28 and 49 divisible by the same number?
No.
I think that it is. Does anyone remember the programming in Desmos to find the GCF?
7.
GCF.
Literally GCF.
GCF. Type in negative 28, comma 49. Everyone should be typing if you can't do this math in your head.
You can do 49.
They gave you 7.
So our GCF here is going to be 7. What else? What else do they have in common? They both have an X. Now, we talked about this forever ago, but if that first term starts with a negative, my GCF also has to be what? A negative. Okay, so I'm actually going to divide here. This is going to be negative 7x, open parentheses, and then we have this actual leftovers. Negative 28 divided by negative 7 is 4. And then x squared divided by x is x. 49 divided by negative 7 is negative 7. And x divided by x cancels out. Yes, sir?
So whatever you get from the GCF, you divide it both of the by?
Yes. Okay. Now don't forget that your GCF actually does have to go in the front. If you ever take out a GCF, it has to be in your final answer. It's in front of the parentheses. Okay, so we're left with 2 terms. On your tree diagram at the top of your paper, if we have 2 terms, what does it say to do next?
Difference of two squares.
Okay, is this a difference? The blue stuff, is it a difference? Am I subtracting? Yeah. Are there 2 things?
Yes.
Are they perfect squares?
Yeah. No.
No. Okay, if that's the case, I'm done.
Yay.
It's not factored.
It is factored technically.
You can't do anything that's not.
Factoring has a lot of different methods and different ways that you could write your final answers. Let's look at the next example there. What do we do first every single time? Okay, does 9m squared minus 64 have a GCF? They're both divisible by 3? There's no GCF here, so we can actually skip that step. But what y'all are thinking of, since there's 2 terms, what should I try to do? Difference of 2 squares. And I already heard somebody say it. Isn't 9 3 squared? Okay, and then we have m squared. And isn't 64 8 squared? Okay, so if I know all of this information, what does it automatically factor to? 3m plus 8, and that's it. I'm done. Put a box around your final answer, smile, and then check your work in Desmos. We still should not be getting these wrong. These are equivalent expressions. Okay, let's do the next one. Is there a GCF between 12x squared, 1x, and negative 6? What, they're all divisible by 6? Even that middle one?
It's all one.
Yeah, it's only going to be 1. So 1 is not really a GCF. Like, yes, technically it divides all of them, but we don't really care. It's not that efficient. So we have to go to the next part of our tree diagram. Does this have 2 terms or 3 terms? 3 terms. So what do? Set up a next puzzle and solve using swing and divide. What number goes in the top? Negative 60. What number goes in the bottom? Wow, that's not right. Negative 72. My bad. What goes in the bottom? And what goes underneath? 12. Okay, 12 and 12. Okay, so we need a number that's going to multiply to 72. So let's make a nice list for 72. What goes on it first? 1 times 72. 2 times...
Everyone has Desmos open, so 72 divided by 2 is what?
36.
What about 3? What about 4? 18? What about 5? No, what about 6?
12.
What about 7? What about 8?
9.
Okay. And that would be my whole list. Phew, that's a big list. Okay. What am I going to be doing with these numbers? Adding or subtracting them? Subtracting. And David is chomping at the bit here to be done. So I would notice that once I did all of these, that the one that gave me 1, or negative 1 really, is this last one, 8 and negative 9. But do I want negative 1? No, I want positive 1. So what do I do? Switch the sign. So it's going to be negative 8 and a positive 9.
Oh my God.
Okay. Oh man, we're making some progress on this. I've set up and solved my X puzzle. What's next? Divide. 9 divided by 12 is still going to be a fraction. 3 over 4. And negative 8 divided by 12 is still going to be a fraction. Negative 2 over 3. I'd have x minus 2/3, x plus 3/4.
You have to swing.
I have to swing the, is that what you're saying, Christian? Swing the denominators forward. 3x minus 2 and 4x plus 3. Whew, and then if we wanted to, we could check this on Desmos to guarantee that we got this question right. Literally, we should not miss this question.
Alex, right, Alex?
I mean, I definitely make mistakes though, so we should still check my work. All right, let's move on to the one on the first one on the bottom row. Okay, first things first, we check to see if it has a GCF. Are those both divisible by something? 2. The GCF is 2. Okay, fabulous. So then on the 50?
Yeah. Only if both numbers had an X.
Okay. So here's what I do after I factor out the GCF. Do I have in blue 2 terms or 3 terms?
2.
2. Okay, so we check and see if it's difference of 2 squares. Is it? Am I subtracting
Yeah.
2 things?
It is.
Are they perfect squares?
Yeah, it is.
Yeah? So if I rewrote this just so I could see the numbers, this is going to be x squared minus what squared? 25 is 5 squared. Okay, fabulous. So we should know how to factor this. The blue part becomes x minus 5, x plus 5. But, and this is where this problem gets important, what was the GCF? 2. You can't forget about my GCF. It actually belongs in the final answer there. If you leave off the GCF, it's super wrong. So don't let your GCFs fly away. They stay in front of your parentheses at all times. I see we have some question marks on our faces. Ask your question. Did you follow the blue part? It's a difference of 2 squares. Speaking of being prepared to do something after taking out the GCF, let's look at this middle one. What do 2, negative 12, and 16 have in common? They're all divisible by 2. Okay, so we're going to take that GCF of 2 out and have some leftovers. Don't lose the 2 that we took out. Why not? Because if you lose it, you have a different equation, no longer an equivalent expression.
But I can always get 5 and 2.
No, you can't always just find a new 2. That's not how math works.
You can buy it.
Sure. Sure, Alex, you can just buy it. Okay, so once we factor out the GCF, am I left with 2 terms or 3 terms?
3 terms.
3. So what do we do to keep factoring 3 terms?
Do it again.
What?
Do it again.
No.
You gotta put a 2 in. Oh, we gotta end that.
We set up our X puzzle. When we do this, we're going to use the new A, B, and C, not the original A, B, and C. So in this one, we're going to multiply 1 times 8, which is 8. The B is negative 6 because we're using the new one. And the letter underneath, A, is a 1 from the new equation. We already took care of the divide by 2. That's just chilling in front. All right, what are the things that multiply to 8? 8 and 1. 2 and... Is there anything else?
No.
Nope. Am I going to add or subtract?
Subtract.
Ooh, why subtract?
Because that's a negative 1.
But remember, we're doing the top one.
Oh, yeah, you're right.
So we're going to add. Okay, so this is 9 and this is 6. Ooh, which one did I want? But I wanted negative 6, so what do? Make them both negative. Change the signs of both. Cool. So we do our divide. We divide. Those numbers come down. This is going to be x minus 2, x minus 4, and I'm done. Or am I?
Yes. No, you're not done.
What did I forget?
Oh, you forgot the 2 at the end.
My GCF has to be in my final answer. You took that GCF out up here. That's great. Make your number smaller. But you still have to include it in your final answer. It's still a part of my expression.
Oh, we're not done yet? No.
That's it. No, now we're done. I had just forgotten the 2.
What about this one? We're doing this one?
Oh, yeah, we're doing that one.
Oh, God. Wait.
Okay, but before we go to the last one, let's take some questions. Thank you. So we're going to walk ourselves through this last one. What's the first question I ask myself when I'm factoring? What's the first box on your flowchart?
15.
Do they have a GCF? What are 15, negative 20, and negative 20 divisible by? 5. Is that the biggest thing they're divisible by? Yes. Okay, so we're going to divide by 5. We will keep it as a positive. The only time the GCF will be negative is if the first term is negative. That was a really good question, actually. So let's do our leftovers. 15 divided by 5 is 3. 20 divided by 5 is 4. And 4 again. Okay, what's the next question I ask myself on my flowchart?
Am I done? Are there 2 square? Wait.
2 terms or
3.
3 terms? And we have 3 terms, so what does the flowchart say to do?
X
Do the X.
X puzzle. With the new numbers, let's set up our X puzzle. David, what goes in the top? Multiply, not add.
12.
Negative 12. Glenn, what goes in the bottom?
4.
Negative 4. Okay.
Negative 4.
And Cristobal, what goes on underneath the bars? Very good. Okay. So here's my number 12. I'm going to set up, got 1 times 12, got 2 times 6, got 3 times 4. Cool, cool, cool. Am I adding or subtracting? Subtracting because it's negative up top. Okay, so we have negative 11, negative 4, negative 1.
You need negative 4.
I need negative 4. Fabulous. Negative 6 and 2. Okay, I can't actually divide the left side. It's just going to stay as 2/3. But negative 6 divided by 3, that's negative 2. To be x plus 2/3, x minus 2. What did I already forget to write down on this question? My GCF. Okay, one last step to be super finished. What is it, Christian? Swing the number forward. Very good. So we only have to swing on one of the two factors. One of the two parentheses. Those are called factors, remember? And we've now written an equivalent expression in factored form is what it's called. And again, since it's equivalent, you can always check your work in Desmos. There's no reason to miss this question. I mean, besides the fact that it's pretty complicated. But once you get a final answer, you should know if it's right or wrong.
What if I'm missing both my arms?
Huh?
What if I'm missing both my arms?
That's a really good loophole to how you would miss this question.
Exactly.
Okay,